All right, everybody. And now we're moving on to investigations 4A and 4B. I'll split this video up into two parts so that you have the part for 4A and for 4B. However, these two parts are actually somewhat interrelated with one another. And the reason why is because both of these really talk about temperature. And temperature is often considered to be the most meaningful weather variable to a lot of people. If you open up your phone, temperature is the first thing that you see on your app. If you ever turn on like your weather app on your phone, or if you go to like a weather page, usually the biggest number like right on the front is temperature. And so this investigation, or this pair of investigations, is going to deal with air temperature. Now with that said, the goals for both of these investigations are first to look at general temperature patterns on a map. Then we're going to talk about the concept of advection and identify locations of warm and cold air advection. And then we're going to talk just for a few moments about the relationship between advection patterns and weather systems. And I'm talking about things like high pressure, low pressure, warm front, cold front, occluded front, and so on. And then in investigation 4B, we're going to apply our knowledge of temperature to an important industry, which is the energy industry, and talk about heating and cooling degree days. And then we're going to talk a little bit about what's called wind chill. So, are you ready? Let's jump in. All right. So, first, let's talk about temperature patterns. So the map that you see on here is probably pretty similar to something that you've seen before. If you've ever been to a weather website, the National Weather Service, weather.com, or even happened to walk in while a friend was watching a weather forecast or looked at a newspaper, and I know that those are all kind of old-timey things, but I can promise at some point most of you have probably seen a map like this. And if I were to take a moment and ask you, okay, identify the warmest and coldest parts on this map, you could probably do a pretty good job at that. So I'm looking here, and at least in the continuous 48 states, you're going to see that word mentioned a few times, continuous 48 states or continuous 48 states. They're just talking about the 48 that don't include Alaska and Hawaii. But with that said, so just for the continuous 48 states, the warmest temperatures, I see a 90 down here, a little 90 over here, a 90 up here. So pretty much the eastern half of the United States is experiencing nice warm weather. Meanwhile, the western half, particularly here across the four corners, so that's Utah, Colorado, Arizona, and New Mexico, as well as much of the Rocky Mountain region. So here's Wyoming. Here's where the coldest temperatures are here in the lower 48. And then obviously the coldest temperatures on the map are up here near up here in Canada. But we're not going to worry too much about that. The only thing I want to bring here is that with this color coding and then with these lines called isotherms, we're able to actually put together a pretty clear picture of temperature patterns. Now with that said, the Weather Studies Manual actually gives you a map with a bunch of different temperatures on it, and then they're going to ask you to draw temperature lines. So draw isotherms, just like the ones you see on here, but there are a few things different. The first thing is that for this map, and for most weather maps, the one I just showed you is kind of an exception, but for most weather maps, we draw isotherms for, let me get a color pretty consistent to their colors. We actually do it for every 10 degrees. We do it for every 10 degrees. And so if you've ever heard like the 50s, the 40s, the 60s, the 70s, like today temperatures are going to be in the 70s or today temperatures are going to be in the 20s. That's why we do it that way, because we draw isotherms for every 10 degrees Fahrenheit. And this is the interval between isotherms. Now with that said, if you were to look at this map and take a moment and look at it, try to identify where the warmest temperatures are and where the coldest temperatures are. I see here the warmest temperatures are down here in Florida. I see a high of 74. And then the coldest temperatures are up near Minnesota, Wisconsin, the Great Lakes, and so on. And so with this said, I don't see any single-digit temperatures, but I do see things above single digits. So we're going to draw for any isotherms that are between between the lowest and the highest. So 10, we don't have anything 10 or lower, so we're not going to draw a 10-degree isotherm, but we will draw one for 20, 30, 40, 50, sorry for my terrible penmanship right here, 40, 50, and 60. And if you take a look at this map, one of the things I'll say is that temperature patterns typically aren't as complex as pressure patterns, and they're typically a little bit easier to draw. However, all the same rules apply. You can't have an isotherm branch out. You can't have isotherms cross, because then that'd give you a place where the temperature is two different temperatures at the same time. But everything else is pretty straightforward. Now, with that said, I would like you to take a moment and kind of practice drawing this. However, I would rather you focus on the rest of the lab. So I'll take a moment and kind of walk you through this, and then we can move on to the rest of the lab. So you see right here there's a place where one location's in the 50s and another's in the 40s. The 50-degree isotherm is going to go right there. And again, just like in lab 1A, you just want to make sure that your isotherm is properly dividing temperatures that are higher in one location and temperatures that are lower on the other side. So this is my 50-degree isotherm. Let's see here. Again, 50s on one side, 40s on the other. So I'm just continuing to do this. Okay. Right here. And I think that's it. Yeah, the 50s go off the Atlantic coast like that. Okay, so there's our 50-degree isotherm. Now if I were to do 40, let's see, I have some locations here with actual temperatures right at 40. So one right there. But again, you're just dividing temperatures that are in the 40s from temperatures that are in the 30s. So very much the same approach. And if you've done the first investigation and you felt a little more comfortable with that, this probably isn't going to be too difficult for you. I'm more just doing this for those that want to see the process. If you don't want to see the process, I totally understand if you skip to a little bit later in the video. So let's see, so that's the 40-degree isotherm. Let me mark that here. So there's the 40-degree isotherm, and up there as well. Now let's see here, between 30 and 11, there's going to be a 30-degree isotherm and a 20, but let's just focus on the 30 right now. Let's see here. So now we're dividing 30s from 20s, and basically you just do the same approach. Over here, the lines are getting really close together. That's what's called a very strong temperature gradient. That means that temperatures change substantially over a small area. So that was our 30-degree isotherm, and then here's our 20-degree isotherm. Just make sure that I do this for a moment, and voila. So 50, 40, 30, 20. And just take a moment and just looking at this map, try to answer the first few questions in the introduction of this text, of this lab assignment. Where's the highest? Where's the lowest? What kind of a temperature pattern do you see? If I really wanted to, I could actually shade these each, shade the 70s in one color, the 60s in another, so you would get a map that looks more like this. But I do think that the temperature pattern here is actually pretty straightforward. So, but of course, if you have any questions, or I just got something. You see, that's what happens when you don't actually edit these videos. Not that I don't edit them, but I think the bloopers sometimes are just natural. But there we go. Let me just fix that real quick. Oh, I just erased the whole thing. That's okay. Let me just redraw it. And I may actually cut some of this video out later. Okay. Now let me redraw it, and voila. And that's actually one of the things, and actually that's a really good lesson to learn. After you draw your isotherms, just double check to make sure that they obey all the rules that we have for them. They don't touch each other. They don't, they separate higher on one side from lower on the other. That they do a good job of not branching out, not doing any of that nasty stuff. The other thing is you always want to label your isotherms. So just in that spirit, there's 40, there's 30, and there is 20. Poorly written, but there they are. Now, what I really want you to be able to do, though, and really the tougher part of this lab, actually has to do with the idea of advection. So, if you've taken Met 10 either with me or with somebody else, you've probably heard about convection. Convection is the vertical transfer of heat. Warm air rising, cool air sinking. That's convection. However, air masses also move side to side. And that side-to-side movement of air masses is what we in the weather world call advection. And advection is the horizontal transport of an air mass. So when advection is occurring, that means that an air mass is moving north, south, east, west. It's not moving up in altitude or down in altitude. Now, if you go back to these isotherms, the way that you can actually identify areas of advection, which you actually can't do right here, but if you were able to, the way that you'd be able to do it is if you had station models. So remember station models? Those were those circular, those little circles with the wind barb that points out of it. Well, in the event that that wind barb, that long pole, is perpendicular or nearly perpendicular to an isotherm, that indicates advection. On the other hand, if the barb, so again that long pole, if it is parallel to a nearby isobar or isotherm, that is no advection. And there are two types of advection. For the purpose of this lab, there's actually like moisture advection and other types of, but for the purpose of this lab, there's two types of advection: warm air advection and cold air advection. And warm air advection occurs when the barbs themselves, so the edge of the barbs, is pointing towards higher value isotherms. What that means is that wind is blowing from warmer air regions. So the wind that you're getting at your location is coming from warmer locations. On the other hand, cold advection is when the barbs are pointing towards cooler isotherms. They're pointing from there. That means that the wind is coming from a cooler air mass. Therefore, it's carrying cooler air with it. And in the introduction section, they give you this nice little, relatively crude map. And I don't want to just give away all the answers here, but I will kind of help walk you through this right now. So the first thing is, if you wanted to identify if a location is experiencing advection or not, what you would do is you'd look at one of these stations, and what I recommend doing is taking the line, taking that wind barb, and looking for the nearest isotherm and identifying if the wind barb is pointing perpendicular at all to it. For example, here at C, the wind is coming from the southeast, and if you were to actually extend that wind barb, it's almost absolutely perpendicular to the 70-degree isotherm. So there is advection happening at point C. The same is true for point D. So over here, if you were to actually extend this out a little bit, boom, there is advection happening there. And then even here at point A or point B, if you were to, again, extend this, and actually point B is pretty much just blatant, like that barb is actually directly perpendicular to an isotherm. Now, what kind of advection do we have going on here? Well, To answer that question, look at where the end of the barb is pointing towards. If you wanted a little bit of help, one thing I've done before using a map like this is I can actually draw an arrow sticking out from this edge, so from like the pole, the top of the flagpole, and point towards wherever that area is. Now, if we look at point D, if we look at station D, if you notice, station D is in a location that's just a little away from the 60-degree isobar, or isotherm, but the arrow's actually pointing down towards the 70-degree isotherm. So at station D, this is actually pointing, this barb is pointing towards warmer air. That means that the wind is blowing from a warmer air mass. That is warm air advection. On the other hand, over here, if we were to do the same thing like at point B, if you notice, station B is between 60 and 70 degrees. If you were to actually extend out that barb, you notice it crosses 60 degrees, then 50 degrees. It's pointing towards cooler air. That is a telltale example of cold air advection. In Investigation 5A, we're going to talk a little bit about how fronts work, and we'll talk a little bit about identifying conditions before, during, and after a frontal passage. But for right now, I will mention that one of the other ways you can identify if warm or cold air advection is happening is look at the position of fronts relative to your location. So here's how fronts work. So right now we have this red line. This represents a warm front, and it has these humps on it. These humps are actually indicating what direction the front is traveling. So everywhere over here, ahead of these bumps, is what we call ahead of the warm front. Meanwhile, everywhere back here is behind the warm front. Now, one of the things you'll actually notice, and this is true in all cases, areas behind a warm front experience warm air advection. Why? Because that warm front is actually the leading edge. It's the front, literally the front, of an advancing warm air mass. So once that front passes, that means that warm air is actually traveling. It's actually advancing right there. So once a warm front passes you, you are now experiencing warm air advection. Warm air is moving in your direction. On the other hand, let's look at stations A and B and talk about their position relative to this blue spiky line. This blue spiky line is actually a cold front. And just like the warm front, those spikes are actually pointing in the direction that the front is traveling towards. Everything on front of the spikes, this is what we call ahead of the cold front. And if you notice, those same areas that were behind the warm front are actually ahead of the cold front. And so ahead of a cold front, you're getting warm air advection. But as soon as you actually pass the cold front, and now you're behind the cold front, you're actually experiencing cold air advection. So ahead of the cold front, warm air advection. Behind the cold front, cold air advection. Now with all of this said, I can't give you the answers to the application sections because then AMS would sue me, and I don't want that. I'm fine walking you through the introduction, but let me at least kind of give you a few hints here. Okay, so the first part of the application section gives you a map like this. And I know that this looks overwhelming, but at this point in the class, we've already started seeing maps like this. Most of what you're seeing on here, you have already seen. You've seen station models, you've seen fronts, and now you've seen isotherms. And so what they actually have you do is they're just going to have you identify locations of warm air advection or cold air advection. So let's point a few out. They actually have you look at Des Moines. I'm not going to give away the answer from Des Moines, but I will give you a hint. This is pretty dang close to perpendicular to this 50-degree isotherm. Another location with a barb almost perfectly perpendicular is right here in Minneapolis. And so it's almost right on the 50-degree isotherm. And if you were to draw an arrow pointing out, over here near where the feather is, you notice that the arrow is actually pointing towards the 40-degree isotherm. So it's actually pointing towards cooler air. That is an example of cold air advection. And actually, if you were to take a look, what do you know? This region here is actually behind a cold front. So voila, cold air advection. Now the last thing that is mentioned, I'm actually going to go back to the previous slide for a second. The last thing that is mentioned is they talk a little bit about advection ahead of high and low pressure systems. And here's how it works. So think about here in the Northern Hemisphere, the way that it works is further north, let me get my little color here. So further north on a map in the Northern Hemisphere, you're getting closer to the poles. And so the poles are going to have cold air. Meanwhile, as you head towards the southern portion of the map, you're actually heading towards warm air. And how does this relate to pressure systems? Well, if you recall, so let me just write warm here real quick. If you recall from the hand twist model, the way that the hand twist model, at the very least, one of the key points of the hand twist model is that air rotates counterclockwise around low pressure systems and clockwise around high pressure systems. Well, here's what this means. Here in the Northern Hemisphere, what we actually get, give me 1 second, I'm actually going to turn on my highlighter here, or not my highlighter, my laser pointer. What we actually get is to the east of a high pressure system, because the high pressure system is rotating clockwise, to the east of it, cold air is actually traveling from north to south. And so typically to the east, southeast, and northeast of a high pressure system, you have cold air advection. On the other hand, on the western end of a high pressure system, now the winds are coming from the south. And hence you have warm air advection on the southwest, west, and northwest portions of a high pressure system. Now as we go to a low pressure system, again, now the rotation is counterclockwise, and so on the eastern half of a low, you have warm air traveling up. So the southeast, the east, and the northeast portions of a low pressure system have warm air advection. And then finally, the west, northwest, and southwest portions of a low pressure have cold air advection. And if you need just to remember, you can come back to this diagram, screenshot it, make it your screensaver, put it on your wallpaper, text it to your girlfriend or boyfriend, and if that helps you remember it, by all means do that.